Today we're going to take notes over work and power. Okay, this is the second set of notes for playlist 4 of our systems unit. So we're going to discuss what work is, how to use and calculate work, and then same thing for power, what it is, how to calculate power. And then you should have some time at the end of the period that you can use to work on playlist 4 task options and checkpoint, or that Center of Math and Systems review homework that I mentioned yesterday is due by Friday, so maybe you want to work on that instead. We are going to be doing a lab in class tomorrow. That is why that note up there tells you to pick it up. The other thing I need you to do today is to complete the knowledge probe before tomorrow's lab so that you're ready to go when you walk in the door. So let's go ahead and get into the notes for today. Starting with a definition for work. Okay, so work is done when an external force is applied for a distance, causing a change in the system's magnitude of motion. Okay, so we do work if we have an external force applied to a system that causes a change in that system's magnitude of motion. The force itself isn't the work. So if I just say, there is a force, that doesn't necessarily even mean that I have work being done. We're going to look at how to tell whether or not a force is doing work later on in our notes today. But the force does cause the work. It's just not the work itself. Okay, it's part of the equation as well, whenever I put that up on the screen in just a moment. But again, work is done when an external force is applied for a distance, causing a change in the system's magnitude of motion. So if I were to, let's say, push a desk in this room, I would be applying an external force and causing a change in the motion of the desk, because it would be going from sitting at rest to being in motion, and therefore I would be doing work on that desk. So how do we calculate how much work we're doing? The equation for work is force times distance times cosine of the angle theta. In this equation, the W, of course, is work. F is going to be whatever constant force is being applied. The D is the distance over which you are applying that force. And then the angle is between the direction of that displacement and the direction of the force. So we're going to look at some images in just a minute that show different angles if you're having a hard time visualizing that. But we're going to be measuring the angle between the direction of the object's displacement, in other words, the direction that it's actually moving in, versus the direction that the force is being applied in. The units for the units for work are Newton meters, and we get that by looking at the equation. We're multiplying a force times a distance. Forces are in newtons, distances are in meters, and that gives us that unit, Newton meter. Now, a Newton meter is also a joule. We've talked about that unit as well when we talked about energy. And so a Newton meter or a joule are technically the same thing, which means that you could report your units for work in joules as well. All right, so I said we would look at angles. So the first one is, what if the angle is 0 degrees? Okay, if there is no separation between the direction of the object's motion, its displacement, and the direction of the force being applied, if they're completely parallel to each other, that would be an angle of 0. And if you were to take that equation, FD cosine theta, and you were to take the cosine of 0 degrees, you'd get 1. And so if you have a force that is being applied in the exact same direction as the object's motion, like in this picture, if he's pushing directly to the right and it's also moving directly to the right, then you can calculate his work by simply multiplying that force times the distance that he pushes it. Because his entire force is parallel, that means his entire force is doing work. And I do have a little symbol up there to show that it's parallel. So this means that I have a parallel force multiplied by my displacement of the box. And again, I don't really need to multiply by cosine theta, because in this case, cosine theta, cosine of 0, is 1. So I'm just multiplying by 1. I'm not going to bother writing that. But I'm going to get a positive value for work. Now, we don't always pull or push things perfectly horizontal. Usually you have an angle, like this next image here. In the next image, you can see that there is an angle separating the direction of the force and the direction of the object's displacement. And so that would be your theta. This picture actually says it's 30 degrees. So if you have an angle that's between 0 and 90, maybe it's 30 degrees, maybe it's 45, maybe it's 60, maybe it's something else. Okay, but if you have an angle between 0 and 90 degrees, then cosine of theta, whatever that theta is going to be a positive number. Cosine of 30 is a positive number. Cosine of 60 is a positive number. And so if you get a positive value for that, you're of course going to get positive work because you're going to have force times displacement times some positive number. Okay, so I will get positive work for this, and of course only a portion of that work, or rather a portion of that force that's being applied is actually doing the work. The only component that's doing work is the parallel portion of it. That's why we're multiplying by cosine theta in the equation. So it will be less work doing that versus the top image, assuming all else is equal, but it will still be positive work. Okay, but what if it is an angle of 90 degrees? Anybody know what you get if you take the cosine of 90 degrees? 0. So guess how much work you're going to do? 0. Because the equation says that you're multiplying FD cosine theta, and FD times cosine of 90 is 0. So the whole thing will be 0. What that means is if you have something like this, where your force is perpendicular to your displacement, you are not doing work. He could carry that box for 500 miles and he would still do no work. Okay? He has to have some portion of his force has to be in the same direction as the displacement. If it's at a perpendicular angle, no portion of his force is in the same direction as his displacement, and he does no work in terms of physics. He'll get tired, but he's not doing any work because that force has to cause or oppose that displacement. All right, here are the other two possibilities in terms of the angles. If it's not those first few categories, we could have an angle larger than 90, but smaller than 180, something like this image here where this girl is trying to keep her dog from running away and she's kind of getting dragged along with him. She's pulling kind of backwards from the dog, but at an angle, the dog is pulling her forward. Okay, and that, of course, is an angle larger than 90 degrees. If you were to take the cosine of some number in that range, the cosine of 130, okay, you're going to get a negative number, which means you're going to get negative work. Okay, on the other hand, what if you pull directly opposite the direction of the displacement? Well, you're going to get negative 1. Cosine of 180 degrees is negative 1, and therefore you'll get negative force times displacement. The entire force is responsible for doing work here. The entire thing is parallel, okay? But now we're just multiplying by a negative 1 because it's also going in the opposite direction. Okay, so that's kind of another little trick you can use when you're trying to determine whether your work is positive or negative. You'll notice that in both of these cases where I have negative work, the force is opposite the direction, or at least some component of that force is opposite the direction of the displacement of the object. They're both trying to pull it back. Okay, whereas if I look at my other ones, I'm going to go back to the other slides real quick. Both of these, some component of their force is in the same direction as their displacement, or maybe their entire force is in the same direction as their displacement. That's going to give you positive work. Okay, if it's opposite, it'll give you negative. You can see it mathematically, though, if you simply plug in cosine of whatever that angle is, and it'll pop out with a negative or a positive number. Okay, so I'm talking about negative and positive work, but work isn't a vector. It's scalar. Those signs that we see, that negative and positive sign in front of the work, is not indicative of a direction. It doesn't mean that the work is going backwards. What it means is that the work is either adding or removing energy, because work is a change in the energy of the system as well. Okay, you can add that to your definition if you want. But you're going to get positive work when the surroundings add energy to the system. You have a positive change in the energy of the system if you have positive work. And therefore your total mechanical energy would increase. So if you had something that was already like a shopping cart, whatever, that's rolling to the right across this room, and you got behind it and you pushed it to the right as well, you're going to make that cart speed up. you're going to do work, positive work, adding energy, specifically kinetic energy, to that system. Whereas if the cart's rolling at you and you push against it in the opposite direction that it's moving, you're going to slow it down. You're going to remove energy from the cart. That would be negative work. One of the most common examples of negative work that you're going to see in a lot of the different problems or in everyday life is friction. Friction's always a force that opposes the motion of an object. Therefore, it always does negative work if it's present. Okay, and so friction always removes energy from a system. It causes the object to slow down. All right, so again, positive work is when you add energy to the system. Negative work occurs when the surroundings remove energy from the system. This means you have a change in your total mechanical energy and that you're probably dealing with an open system, okay, where you're having a change of energy, free exchange with the surroundings. All right, so let's go back to those forces at an angle. If a force acts at an angle to the direction of displacement, something like this. Okay, so here's the displacement of my object, or the direction that it's moving right now, and it's going to be displaced. Here's the direction of the force that is applied to it, and so obviously I have a force at an angle. Okay, then you would need to start by figuring out how much of that force is horizontal and how much of that force is vertical, because when we are dealing with forces, forces are vectors, and when we are dealing with that, we do want to take a look at what those components are. And look at what's happening with my vertical force and what's happening with my horizontal force. So let's start by looking at that horizontal force. If I wanted to solve for this component of this overall force, F, I would need to use cosine, and I would say that the cosine of my angle theta equals my adjacent side fx over f, which I can rearrange to get this. And so my x component of that force is f times cosine theta. And whenever I go to plug it in, and if I wanted to solve for that work, looking just at the x direction right now, okay, I could say that the work done by fx would equal fx times the distance that this thing moves times cosine 0, because this fx is 0 degrees from my distance line. They're parallel. Okay, and so that would tell me that the work done by that force is simply that amount of force times displacement. Okay, so the horizontal component, the entire thing's doing work because the entire thing's parallel. Cosine of 0 is 1. Okay, the whole thing does work. But if I look at that y component, okay, again, I could find this y component if I wanted to solve for it. If I had some numbers, I would need to use the sine function, and I would say that sine of my angle theta equals opposite over hypotenuse. That's fy over f, and if I rearrange it, I get this. So if I wanted to look and see if there was any work done looking at that force in the y direction, so the work done by the force in the y direction would equal my force in the y direction times my distance or displacement that I have here times the cosine of the angle of separation. Well, this is a 90-degree angle. This force is applied up. The displacement is to the right, and so the angle between the two is 90 degrees, which I already know. What's the cosine of 90 degrees? 0, which means that force isn't doing any work. Again, we already talked about this. If you have a force that is perpendicular to the displacement of your object, that force does no work. So if you have a force at an angle, only the x component does work when your displacement is in the x direction. Of course, if your displacement was in the y, it'd be different. But you might have drawn it differently too. So only one component of that's going to be doing work. In this case, it's the x component, and that entire component does work. But again, not this entire force, just this piece of the force. All right, so what if we have a graph? Okay, so this is a force displacement graph, an fx graph, and I have here some amount of force F being applied for some amount of distance x. And if I wanted to determine how much work that is, again, work is force times displacement times cosine theta. We're going to assume that this force is parallel to my displacement. So that's what it says here. F is the magnitude of the parallel component of the force to the direction of the distance. We have to assume that, or it has to be told to you. Otherwise, you can't do anything with this unless you know that angle. Okay, so we're going to assume that this is just the parallel component. And so if I wanted to determine how much work this parallel component is doing, again, it's just force times displacement, which in this case is my y-axis multiplied by my x-axis. It ends up being length times width of this rectangle. So I can find the area, and that's always going to be the case. If you have a force displacement graph, the area under your line on your graph, or the area under the curve, if it happens to be a curve, will be equal to work. Okay, so work is the area of a force displacement graph. And that's true even if your force is changing. This one's not a rectangle, it's a triangle. Same idea, let me show you why. If we have a changing amount of force, we're still going to do the same thing, because now our work is going to be our average force times our distance. Well, guess what? My average force is going to be half this max value for F. If I go from 0 to 100, my average would be 50. Okay, and so if I wanted to solve for it, I'd have half that max F times displacement, and guess what? That ends up being 1/2 base times height. This is the formula for area of a triangle. So again, if you have a force displacement graph, no matter what shape it is, find the area under it, and that will represent the amount of work that is being done. Okay, so area of that type of graph is work. All right, so let's talk about power. Okay, so I told you our notes today were over work and power, so this is the second part of those. Power is the rate at which work is done. So obviously, you have to have work done in order to be able to calculate your power output, because if you have no work, you have no power. Okay, so, and you'll see that with the equation as well. The formula is power equals work divided by time. That's what it means when we say the rate at which work is done. It's how much work do we do per second, or per whatever unit of time. Typically it is seconds though. And so I have work divided by time. Now I know that work is also equal to FD cosine theta. So by substitution, I could derive this equation. I could say that power is equal to FD cosine theta over time. That is also an equation that I might end up needing to use depending on the information that I've been given. You'll notice that I highlighted two of the variables in my equation, distance and time. Anybody know why I did that? What is distance over time? Velocity. So I could also get this equation. That's another equation you could derive from that. Okay, so power is equal to work over time, which is FD cosine theta over time, or maybe you have velocity instead of distance and time, or instead of work, and you might need to do force times velocity times cosine theta. Okay, again, you should be able to derive any of these equations depending on what you need for whatever calculation you're trying to do. The units that you're going to get for power, again, work is in Newton meters, time is in seconds, so Newton meters per second. Now remember, a Newton meter is also a joule, so joules per second is also correct. But the standard SI unit that we use is called the watt. Okay, so watts are the same thing as a Newton meter per second or as a joule per second, and we can abbreviate those with a capital W. So when we measure power, it is typically measured in watts, which you probably associate more with light bulbs and hair dryers and microwaves than you do with this, which if you do end up taking AP Physics 2, or whenever we have our very short unit at the end of the year where we have to do circuits, you'll see watts again. All right, so let's do a calculation. This one says a 30 kilogram block is pushed by a 100 Newton force, causing the block to move to the right 5 meters in 3 seconds. What is the power when the force is applied at 0 degrees, at 30 degrees, and at 90 degrees to the direction of the block's motion? So this is like 3 calculations in one, because I'm asking you to solve for it with 3 different angles. Okay, and so first things first, we need to set up our system so that we have the ability to calculate power, which means we need to set up our system so that there is work being done, which means we need to set up our system so that there is an external force acting on our system. Okay, so it doesn't say what's pushing the block, but let's say it's a block and a person. I wouldn't want my system to be the person block system, because I need that force to be external. So my system needs to be defined as just the block. That way I can have an open system where I have a transfer of energy, I have work, I can find power. Okay, so let's take a look at what information we know. We know the mass of the block is 30 kilograms. We know the force applied to it is 100 newtons. We know the distance that the force is being applied is for 5 meters and that it's applied for 3 seconds. We're trying to solve for power. But again, we have 3 different calculations because it's telling us, hey, this 100 Newton force, we're going to apply it in 3 different ways. We're going to do it 0 degrees, 30 degrees, and 90 degrees. So let's go ahead and work them out one at a time, starting with 0 degrees. Okay, so first things first, we need to start with our equation. We're trying to solve for power. Power is work divided by time. I don't know the work because I don't have that in my list of givens, but I do have a time, and I do have an equation for work that might help. I know again that work is FD cosine theta, so power is FD cosine theta over time. Again, we derived this equation just a minute ago. Now I have variables I can plug in because I have force, I have distance, I have time, and I'm about to do this same calculation for 3 different values for theta, starting with 0 degrees. Okay, so first calculation looks like this. If I have an angle of 0 degrees, my power would equal my force 100 newtons times my distance 5 meters times cosine of 0 over 3. And again, cosine of 0 means that my force is parallel to my displacement, meaning the entire thing is doing work because cosine of 0 is 1. So it's just going to be 100 times 5 divided by 3, which is 166.67 watts. Okay, so if my force is applied parallel to this direction of motion, then I have 166.67 watts of power expended. Let's try it now at a 30-degree angle instead. If I do this at an angle, I'm expecting less of my force to be doing work because it's not parallel anymore. Only a portion of it is now doing work. And again, I can find that by multiplying 100 by cosine 30. It's already built into my equation. But I'm expecting a smaller power output. And I get one. When I solve for this one, this is a smaller value, 144.34 watts. I have less power whenever I apply that force at an angle. Okay? And again, you see that mathematically as well. Last one is at 90 degrees. What's going to happen if I try this at 90 degrees? There's not going to be any work. Again, you can plug it in, but cosine of 90 degrees is 0. And I'm multiplying by it, so I have 0 work. Okay, are there any questions about this calculation? Not yet. Again, you're going to have some like this in your task options, and that's one of the things you could be working on for the rest of the period. So for the rest of class today, you are working on either playlist 4 or that Center of Mass and Systems review homework that is due by Friday. Additionally, you do have a roller coaster Q&A day next Tuesday, and you are actually doing the roller coaster. Is that next week? That might be the week after. I have to look at the calendar. But you need to, if you're planning on building something in class, bring some supplies. Some of you might be building it at home and testing it there, and some of you maybe can't get together, and so use the class time. But if you're trying to build something to test out, you need to bring tape or something to actually be able to construct it. I do have some insulation. If you weren't able to find some, okay, you're welcome to use the stuff that I have in here. But that'll be your group's insulation unless you bring in your own. And it needs to stay in the room. So, but anyway, you can work on that or have a discussion real quick about who is going to bring in some of that stuff so that you can test it if you would like to. You do have a bump assignment due date coming up in less than a month. And then tomorrow you have a lab. You picked it up. Hopefully you have looked at it. If not, look at it, because the other thing I need you to do is the knowledge probe on there, but that lab is going to have you going up and down the stairs tomorrow. So I'm going to very strongly encourage you to wear tennis shoes or some shoes that you are able to run or walk in without tripping. So flip-flops, Crocs, high heels, probably not good options. Okay, wear something where you can move up and down the stairs easily where you won't trip, because that is part of your lab. You're going to be figuring out how much power you have as you go up and down the stairs. So some people choose to like race each other, which is fine, but wear tennis shoes, not Crocs, okay, if you're going to be running on the stairs. All right, so anyway, if you have questions for me, let me know, but I'm going to let you guys get to it.